So good afternoon. I'm privileged to be part of this discussion. It's actually the first time I'm having the opportunity to discuss ultrasound related knowledge with non-medics, because the approach will be different, because the purpose is different. So I would like to appreciate the CEO for inviting me to do this, and this is an opportunity I'm excited about, and it's an opportunity I do not take for granted at all. So I'm going to be discussing for the next few days sonographic principles and instrumentation, as it will be relevant for the Smart Bra project that is already underway. So we need to understand some principles for which I believe will be relevant in your developmental process as you go ahead to achieve this feat, which I know is possible. Like I said, anything is possible. So my name is Godwin Agadanegidu, and I'm a sonographer for more than 11 years now. So why we should study ultrasound physics to achieve this goal? I believe that basic knowledge of ultrasound physics is vital to correlate the application of ultrasound for diagnostic and therapeutic interventions. Well, in this case, we're looking at diagnostic intervention. Image acquisition is highly operator dependent. So the device really produces for you the images that you made it produce. There are certain rules you have to obey, maneuvering skills you need to have to be able to produce certain images. Knowledge of physical attributes of ultrasound waves and image generation is critical to recognition of artifacts and prevention of misdiagnosis. So artifacts will be produced because of the behavior of sound, and that may pose some certain challenges, but there's a way around it using artifacts to help with diagnosis. That will be discussed in other platforms and opportunity, but in this case, we want to prevent misdiagnosis. But first, let's look at ultrasound modes. There are different modes, but here we're going to pick, we're just going to peep into two modes for the project's sake. So we have the A mode, which is amplitude mode, but popularly called A mode, and this is the simplest type of ultrasound. In this case, a single transducer scans a line through the body with echoes being plotted on the screen as a function of depth. So it's actually a echo intensity or amplitude against a time graph. But in this case, we want to see the depth and the strength on a graph. So the scan results in a wave spike or peak interface between different tissues. So the closer the obstacle, the stronger the amplitude. The farther the obstacle, the weaker the amplitude, and you see those spikes. Every spike will represent the intensity of the echo that is returning. However, you need to know quickly that therapeutic ultrasound usually aimed at the specific tumor or calculus to allow pinpoint accurate focus of destructive wave energy. So you can use ultrasound wave to destroy or break down calculus, large calculus, for therapeutic purposes, and also it has also been experimented where specific ultrasound wave energy has been used to try to destroy wayward cells, tumor cells. But it's just for the knowledge, not for this purpose at this time. So right here we have an image of the A mode. This is to actually give an idea. So we have your, for example, you have your transducer on this end, and you have obstacles or objects of the same consistency, the same thickness and stiffness. 3 of them placed in an array, and we are passing through we're passing the ultrasound wave through from the first to the last. So if we plot that against the A mode screen or the graph, we have echo intensity on the side, depths with respect to time on this side. So what we see is the first obstacle, with the first object, will have a stronger amplitude, stronger intensity, because it's closest to the origin of sound, which is the transducer. So we have a stronger echo returning. Now, due to reflection and refraction and all those things, attenuation occurs. Then a weaker ultrasound gets to the next one. So much weaker echo is returned because there are also losses as the echo travels back and scatters. And as it gets to the last obstacle or object, it gets even weaker. So you can see on the graph, you have a stronger amplitude from the beginning, weaker, then the weakest at the end. And you can vary that with frequencies, and you see, but basically, just to give you an idea that as sound travels and encounter obstacles, attenuation occurs, and we should be able to understand why the echoes that are returning are weaker. The other mode, which is generally in use right now, is the B mode or brightness mode. The brightness mode produces a 2D dimensional image of the underlying tissue. The use of the grayscale imaging ultrasound has shown the 2D image in which the organ and the tissue of interest are depicted as points of variable brightness. So each brightness or bright dot will represent an echo. Yeah. So on the scale for bright mode, it is actually a 2-dimensional image you're going to have, the length and the breadth. Then all the echoes returning will be represented as dots of varying brightness. In fact, 64 shades of gray is used here. So the brighter, the stronger the amplitude, the weaker, the lesser the amplitude. And in areas that are dark, there is no echo returning at that point. Now we look at modern diagnostic ultrasound systems. The operating principle behind our modern ultrasound system is really not complicated. It operates on the pulse echo ranging technique that uses piezoelectric crystal to transmit short pulses of sound into the body, then receives reflected sound or echoes, and display that echo data in real-time 2D grayscale images. So the piezoelectric crystals use the principle used in sonar, that is the pulse echo ranging technique, to produce images of the body. The piezoelectric crystal in transducer, what they do is they convert electrical voltage into short pulses of high frequency. The transducer is usually coupled to the body, to the skin, of the person being examined, and the pulse is transmitted into the body, into the tissue through a straight line. Now, one of those factors that produces the echo back, those bright dots you see, is due to acoustic impedance mismatch. Now, it's basically the tissue difference in the body that produces these reflections, which are sent back to the transducer. So at the transducer, the piezoelectric crystal converts the echo back into small electrical voltages. So that conversion brings about the echo signal, the tiny echoes that are converted into a signal is called echo signal, and this echo signal will be evaluated in the machine based on two broad criteria: echo strength, or the amplitude of the echo, and time. Echo strength is used to assign the brightness. So how bright it will be will depend on the amplitude, the strength of the amplitude on a grayscale. Then where it will be located will be dependent on the time it returns to the machine. So in echo signal processing, what happens is that echo signal that is received in the transducer is now sent to a receiving circuit. We call it a receiver, but we know it's an amplifier. So what it does is, because the strength of voltage that is sent from the pulsar to the transducer is larger than what we received, because echoes are usually lesser in frequency than the original pulse. So therefore, the voltage it will generate in the piezoelectric crystals will be tiny. So we need an amplifier to amplify the echo, that information. Now when that is done, it's moved to the system's memory. In the system memory, there are two things that happen. In fact, I would like to put it back to back. On this side, the writing of the information that is coming from the transducer, and on this side, the reading. So on the writing part, those two criteria plays a big role. Echo strength. The memory allots brightness based on the 64 shade of gray. Then the same memory allocates, or rather reads, the timestamp on it. Then allocates locations. So this is done, and when enough information has been collected to make a complete image, it is written on the other side of the memory, where it is further sent to your TV, archiving, printer, or whatever you have. But this whole process of writing and reading is done within 1/20th of a second. So it's pretty fast. So once enough data has been stored, the data is read, like I said, from the memory and sent to your display, your printer, CD-ROM, or hard disk. The entire process happens so quickly, the system is able to generate a real-time display at a frame rate of about 30 frames per second. So you will not have this flickering image because it's pretty fast. So when it's gone, when it's read into all other issues like your printer, the monitor, and all that. That's the end point of all those information. So basically, the component of a basic ultrasound system is the pulsar, the transducer, the receiver, the memory, the display TV, and recording devices. Now, this image shows the interconnectivity of all the components, how they relate with one another, from the pulsar, which we also call the transmitter, to the transducer, back to the receiver, memory, and display or recording device. Now, the pulsar, what does it do? How does it do what it does? The pulsar produces the electrical voltage bursts that are sent to the transducer. The voltage burst, I said, because it does not send a continuous electrical voltage. What it does is it sends short bursts of voltages that goes to the transducer. So in response to each burst, the piezoelectric crystal in the transducer vibrates to produce a pulse of ultrasound. Typically, the pulsar may produce or send up to 10,000 voltage bursts per second. That's pretty fast and pretty large, which we equate the amount of frequency bursts or pulsation that will be happening at the transducer. So at the transducer, which contains the piezoelectric crystal, so in response to all those voltage bursts from the pulsar, the crystal in the transducer will vibrate, convert the electrical voltage into pulse of ultrasound. Now each voltage burst from the pulsar produces one pulse of ultrasound. Each voltage burst, one pulse. So if it's 10,000 bursts, it's 10,000 pulse of ultrasound. After each ultrasound pulse is transmitted, then the transducer then starts to receive the returning echoes produced by that pulse. Now, upon reception of each echo, this transducer vibrates again to convert the echo into tiny electrical voltage that is called echo signals from the transducer. Then from that transducer is sent to the receiver, like I've said before. Now, remember what I said about the receiver? It amplifies the echo signal so that it can now be written in the memory or the scan converter. So the two parameters is time and strength. That's what it does. Then you allocate it in pixel or pigeonholes and allocate a binary number on it. Wherefore, once all the echo data for a complete image has been stored in memory, the data is read and it goes straight to your display. And your display, remember this is 4 shades of gray. Now what we have is that strong echoes are white, mid-level echoes are gray, and very weak echoes are almost black. There is no black echo. Where there is blackness or complete zero echo, well, complete dark shade, it means that there is no echo returning. So there is nothing there to reflect. So ultrasound system produces real-time sequential display of grayscale image with a frame rate of 15 to 30 frames per second, so that our eyes can perceive a flicker-free, continuous real-time image. And I've told you about the recording devices like a printer, your CD-ROM, a pen drive, and all that. Thank you very much. We'll see you in the next class of sound wave and sound parameters. So see you then. Thank you.